Okay, perfect. So everyone, thanks for, first of all, Jimmy, for organizing this. This is really great and a good opportunity to connect with everyone related to computer vision field. And I was glad to see you, Chinli, and it's been a while actually we didn't connect, so it's great to be connected here. So first of all is I'm just going to talk today about these objects and image localization from visual data. This is kind of a very new and old field that is actually kind of very challenging and is kind of has a lot of applications in the computer vision applications and many other applications related to it. I am associate professor of computer science at University of Vermont. I studied my PhD in 2012 in SUNY Buffalo, and I joined Palo Alto Research Center and Xerox Company from 2012 to 2017. Then I joined University of Vermont as assistant professor. Now I am associate professor there. And I am now a Fulbright scholar in Jordan now. So I'm talking to you from Amman, Jordan. It's a little bit late here in Amman, Jordan. So it's 10:30 p.m., just feeling sleepy, but having fun listening to all these great talks. My main research interest intersects between the machine learning theory and application for image and object understanding across various modalities, especially between satellite and ground imagery. And there is a lot and a huge potential for this kind of applications, especially now with this satellite imagery is being available as an open source for many applications, and there is many daily satellite images are available, and using this kind of ground to satellite and satellite to ground is very, very useful in different domains. So my main research questions that I'm trying to answer is for any given image, where on Earth it is located just by looking at the visual information, no geotags, no and any other helpful information. So that is what is that simple question that we are trying to answer. And when we say like located, we mean like where's the GPS location for this image. And the second question is if you localize that image on the map and you detect the objects inside the map, can you localize these objects on the map itself? So that is actually kind of two questions. First is where's the image is, and the second question is where those objects inside that image on the map. And those you can think of it, there is a lot of applications for this kind of two questions. The first one is we know that the GPS error is really huge, and just using those visual information as a reference to guide us through and navigate through like this kind of noisy GPS information can be useful or not. That would be great if we can narrow this down to a small error rate less than the GPS error itself. And also the second question, there is a tons and a huge application for that. For example, like understanding all the objects on the world and localize them on the map. Imagine how much you can use this information for different applications. For example, if you want to localize the signs, road signs on the map, you can do maintenance for those signs across years, and you can add the quality for those road signs and provide them for example, like transportation departments and so on. So where we are on this in my lab is we are the state of the art for answering these two questions. And this is actually kind of very exciting for us to share what we've been doing in the last few years. And actually all the credit go to my students in my lab, Xiaohan Zhang and now there is Dan Wilson and Ahmed Rabi. I think most of them in this talk, and hopefully they can help us in answering some of those difficult technical questions if you have some of those. So in image geolocalization, there is actually many terms of that. There is what we call semi-view geolocalization, there is cross-view geolocalization, and there is object geolocalization. So we differentiate between, this kind of image geolocalization and object geolocalization. But also there is what we call in this image geolocalization, we have this scene and a cross-view. So in this, how we define this kind of the same view geolocalization or the geolocalization itself. So we deal with it as a retrieval problem, which means I have a database and I have an image. I'm just trying to find the correspond that image that in my database that looks like similar to my image. So I know that image GPS information, so I can look for it and simply I can navigate my GPS by just retrieve the right image. If we are going to use the same view geolocalization, which means we need tons of images collected from every single road in the world to correspond that query image with the one on our database. So this is going to be really hard and tough to achieve. Instead, people start using what they call cross-view geolocalization, which means we have the ground image, but we have access to most of the satellite images on Earth, and we can search on these satellite images instead of collecting those ground images and try to do same view matching. But those kind of cross-view image localization, which simply is a query and reference database, has like a lot of problems. And the first problem is there is a drastic view changes. So this image is this one from the aerial or from the satellite view. So, like it's not easy to find this kind of correspondence between the two images. And both, for example, like in most of the databases or data sets available right now, they are not captured at the same time. So the satellite image could be captured today, but the ground images could be captured actually at maybe like a few days or few months or a few years ago. And also there is different object resolution. So even these satellite images that we have access to, they have different resolutions, maybe 10 meters, 3 meters, or maybe more. So the problem become even more challenging as we move forward. So this kind of now what I'm gonna talk more about in this talk today is mainly I will talk about this cross-view geolocalization because it's more kind of interesting topic. And also, there is a lot of things that we can achieve in this one. But also we did a lot of other work in object geolocalization that I'm having it as actually as a paper reference. And maybe I can open a demo or so just to discuss this and show some fun at the end. Even though there's a great progress in the computer vision field, achieving a high accuracy at some point in the same view, in the same area for the image geolocalization, but there is many open questions still in the field. For example, like now we don't have any explicit model that correlate between the cross-modality spatial information. What does this mean? This means that can we, because the main correspondence between the ground and aerial images, these kind of objects like the street, buildings, objects that could be correlate between the ground and the aerial images. And we don't have this kind of explicit model correlation between the two. Most of the model these days, they do what we call the implicit correlations. The second challenge or the second open question, we don't see much of sequence of images correspondence to an aerial image because typically people actually kind of capture in a sequence of images, and this sequence of images could be more informative to localize the image location or the current location, so you can use those information. So we actually presented a paper in likely to 2022, I guess, about this kind of sequence of images, and can share the links below. I have some slide, but I don't think I have time to it, but we will be lucky if we can talk about it. And there is some advanced cross-area performance. This is also an open question. Most of the data set that existed now in the algorithms, they focus mainly on the same area. And cross-area performance is very, very poor now. Compared to the same area, we reach kind of more than 95% accuracy on the metrics that we use, but on the cross area, on the cross area is like around 50s or by the end of 50s. So very still, this is kind of a very open question, how we can achieve a kind of a scalable model that can tell us on unseen area where is the image being localized. So all these kind of open questions are kind of very, very challenging. So today, just gonna explain one of our talk at Triple AI paper that we presented 1 year ago. And this paper is like kind of tried at that time to model they just call it this kind of explicit correspondence between the ground and the aerial with this kind of explicit correspondence. So currently, most of these methods that we have is CNN-based methods, and those CNN-based methods, as we know, they do kind of local correlation among the pixels, and also, you know, like because transformers has been commonly and publicly, you know, like being used in different places in computer vision, we will start to use this kind of transformers, and those methods also still implicitly doing this kind of modeling for this spatial information. And therefore, this kind of cross area benchmarks actually degrades a lot. And for this work that we presented in Triple AI is we want to have some kind of explicit correlation. So our model, when we presented that time is actually taking the CNN features and we implement what we call the geometric layout extractor, and we produce what we call the feature P or the descriptors, or what we call them the geometric descriptors. These geometric descriptors are compared with those kind of features, and we multiply them in kind of a dot product to produce this kind of the final F feature that hopefully will represent, you know, that kind of the correspondence on the geometrical side of the features. So in here, like to be more specific, we proposed what we called it the GeoDTR architecture, and we also proposed for the first time some sort of augmentation for this kind of research, because most of the augmentation methods that's been existed wasn't actually designed to this kind of correspondence between the different modalities, I mean, between the ground and the aerial. And also we define what we call counterfactual learning schema. That is something that will hopefully train the correspondence between the ground and the aerial images to capture this kind of geometric correspondence. So what we did in here is we want the finally predicted F feature is to produce you know, this kind of correspondence between the two signals, and hopefully will make learn the geometric layout descriptors. So first we look at the geometric layout extractor, and geometric layout extractor is used to distinguish low-level information and generate a bunch of layout descriptors to capture the spatial information. It takes a raw feature R as input, and then we have it to a max pooling layer among channels applied to obtain a saliency map M. And then from that, then an embedding layer projects the M's into K subspaces. And here K will be the number of the geometric layout descriptor, which will be discussed later. And then the combined with the customized index aware position encoding and key embedding vector can have the input tokens to E to produce the transformer, so to feed the transformer and explore the correlation in E. So after the transformer, another embedding layer has been project the output back into the original space and produce the geometric layout descriptor B. So let's now talk about this counterfactual based learning process. As described before, like we use the geometric layout extractor to produce the geometric layout P from the raw feature R. And so this we just produce P from R, and we just have the dot product between the two to get the F. And then after that, we most importantly step in this because, like just explain in this way, we don't have this P, the groundwork for P. So to train this P and try to get this kind of geometry correspondence between the two in both modalities, we want to replace the learned geometric layout descriptor B as we do with a B hat, which is kind of imaginary descriptor B that's sampled from a normal distribution. So the idea is we can further produce an imaginary latent feature F hat by B hat and R. And this time there's no correlation between R and B hat. So this one is not correlated to B hat, which is good because in this case, we can treat F as an obviously wrong solution. And we can, and we expect that F can be further away from F hat in the latent space. And that is what we want to achieve, is to maximize the distance between F and F hat. And hopefully we can learn this correspondence between the B as a geometric layout. So, and before we dive deep in the next is, we usually break this correspondence between the aerial and this kind of aerial ground pairs as uncapable to provide diverse layouts. And that's the problem is when we do what we call this kind of data augmentation. So data augmentation in general, people currently, they don't use this kind of correspondence when they do any sort of data augmentation in one view, they don't apply to the other view. So what we do is, for example, like this one, if you just mask these two parts here, how this will be correspondence on the aerial image. So you need to also to mask it in the same way on the aerial image. So, and also there's no sufficient attention on the low-level details. So in what we did here in our paper is we introduced what we call it the LS techniques for data augmentation. The first one was the layout simulation, and the second one was the semantic segmentation. In the layout simulation, layout augmentation, we want to keep the correspondence and also maintain the low-level details. So for example, like in here in the rotation, whenever that you rotate the image in the aerial image, then you have to do the same kind of rotation in the ground image. The same thing for the flip. And most notably in here, if you come up with different kind of combination between the flip and the rotation, you can actually increase the number of the image in your data set, and you can basically train a better model to do a better correspondence. And also for the semantic augmentation. And also it's worth to mention that, like each data set currently, and this is something that Jenny, we can talk about it later on. Most of the data set now, they kind of very specific. They came from one certain region and they kind of associated with a certain satellite appearance and, kind of characteristic. So for example, like the satellite could have some certain brightness, some certain contrast, and so on. So basically those images will be correspond to that area, to that specific, appearance of the satellite. And to remove this kind of contingency between the two, we are trying to provide both, the aerial and the ground images with different brightness and contrast saturations, all these kind of color and luminance, chrominance, blurring, saturation, all of this kind of data augmentation on both sides, both modalities with just kind of randomly. So we can create more and ask our algorithms to focus more on the geometry more than the appearance. So with these two, this kind of very few examples about those, as you could see. And before we move to our model and the training, so we have this, what we call it, the two losses. The first one, which is called the counterfactual loss that we talked about. So we have the F and F prime, if you remember, and we try to maximize the distance between the two if they are coming from different. You know, they are basically they are wrong samples that we want to maximize the distance. And we didn't talk much about this triplet loss, which is basically is a common in the field, and that's the way how they try to you know, maximize the distance between the similar samples using this kind of triplet loss. And what we did in here is we just achieved this by you know, taking a you know, like an account both losses for our main loss. And in the implementation details, we use the ResNet, which is kind of a light one for our backbone, and we use also our alpha and beta 10 and 5 respectively. I didn't maybe mention in the previous slide that here there is no kind of constant to give a weight for each, because we have the beta and alpha that we can play with, and they can give us a weight for those kind of two losses. So we use the 10 and 5 respectively. That's the best that we could find. And also the model is trained on one single NVIDIA GPU. It was actually the descriptor scale is set to 8. And our code is publicly available that you can take a look at. There is actually two main data sets in the field now. There is the CVUSA and there is CVACT. The CVACT is more challenging because it has more testing pairs. And also this could be the evaluation metric, the way, because it's kind of a retrieval problem at the end. So you have the image and you have all the satellite images in your database, and basically you just do the retrieval task and you rank all the output, and if it is the top one, then you will report the top one. If it is type 5 and top 10 and so on, or top 1%. So our model, currently we have the CVUSAE, the same area. And you maybe just think about the same area, because again, same area means now that we achieved kind of the results on the top one is around 95% plus. This is kind of very great, right? But same area means something, but doesn't mean the cross area. And we're gonna look at the cross area, how it looks like. The top 1% is kind of, and top 10 and top 5 is kind of very, very high. So same area kind of can tell is kind of a solved problem, kind of sort of solved problem. But and also here, like kind of CVACT, same area. As you could see, the top one is around 86. I think like this one is more challenging data set. And also, as you could see here, the cross area, this is where is actually the models become more challenging. As you could see in here, the top one is 53. And we are the state of the art, true, but this is kind of still far away from getting advanced, and still there is a long way to achieve a very good models that hopefully can scale. As you could also see in here, there is training it from CVUSA and applied to CVACT, or the other way. Again, you know, like this is kind of very challenging. And more kind of and I think we should put more weight on this area of research more than the same area. And also in here, maybe someone would say, you did the data augmentation, you might be the data augmentation achieved a better result. So we did kind of ablation study on our model. And our model showed that without any sort of data augmentation, we still the state of the art. That is something in here. With the data augmentation, we are actually kind of achieving everything. But look at this results in here. With the data augmentation, we are achieving 53. Without data augmentation, it's kind of 47.79. So there's a big gap and a huge gap in here. And the same thing actually at this point in here, without data augmentation, is 29. And this is kind of more challenging data set. As we could see here now, it's 44.07. And compared to other models, it's very large gap between the rest. And the good news that when we visualized our descriptors or the geometrical descriptors that we had, which is those kind of the B's. So if we have the input image, I'm not going to talk about this. This is actually with what we call it a Boolean transformation. So typically the Boolean transformation is something that we do as a pre-processing step. Typically people, they do it so they can enhance the results. In here in our model, we did the both experiments with and without the Boolean transformation. It's kind of very interesting to see the ground image descriptors. I mean the geometrical descriptors, the B's, from both the aerial and the ground, and they look very, very close. This is the difference between the two. What does this mean? This means that our model is kind of learning this kind of geometry correspondence between the two modalities, which is really great. And this is kind of, this proves that our model is really working well. Yeah. Yeah, I think this is something already being captured. So let me share my screen to different. Do you see my screen still?
Yes, we still see your screen. We see your desktop.
Okay, let me try to share. I didn't talk about object geolocalization, but I'm trying in here to motivate you guys on that. So in here, I hope you're seeing a website, right? Maplizer, right?
That is correct.
Okay, so there's the demo here. In this demo, we have an images that came from Vermont, Burlington area. And in this one, you can basically see all the traffic signs on the map. You can click on any one of those and you can check it on the map, see it on the images. And this has been actually processed by our algorithms that do object geolocalization. This is kind of just, I'm going to shed the light on this kind of important object geolocalization research, and its application in different fields. This is one of them. So in Vermont, in here, for example, like let me see if I have a big data at this point. So this is the whole Vermont area with all the traffic signs that's been localized in all the state. And that's kind of now become more related to commercial product that came from our lab. So with that, I'm just gonna end my talk with this nice looking slides, and I'm happy to answer a few questions if there is some. And descriptors, how many output do we have? So I think if I'm gonna go back, I think we had the descriptor size. I didn't get I don't recall the exact number actually, but I think it is more at least 128 plus, at least. Shawhan, if you remember the exact number, please post it here.